All right, thank you, Henry. Our last presenter is Gary Harbison. He's the president of HLG Consulting Engineers in Santa Rosa, California. He started his career with Marley here in Kansas City and has a bachelor's degree in mechanical engineering of Missouri. Gary is very involved in TC 8.6 and 3.6 as well. Welcome, Gary.
Thank you. Thank you. Good morning. Yeah, I was very fortunate, when I got out of engineering school, that my first job was with Marley here in Kansas City, and they sent me off and set me on my world. So with that, I want to get started here. Some of the learning objectives, just clarification on how design really of condenser water systems, the system itself and the pumps, and then various sump piping, how that affects water treatment. Here's our two friends that are come with us, Mr. Blue on the left, and on the right is, I say that Mr. Green because, as you can tell in that sump system, there's a bit of green slime growing underneath him. So these are our two buddies that will be hanging out with us today. Just true fact, I think, steal from one person is plagiarism, but from many his research. Josh taught me that early on, I think. And really, the biofilm is our enemy, and as we've talked here, the stagnant water, which I'm going to address, is really where biofilm likes to hang out. So here's our matrix, and the protozoa eat on the bacteria. Some of that bacteria is pathogenic, Legionella, Pneumophila, and then the amplification that takes place inside the protozoa as and then released as amplification is the same effect that we have when the humans inhale Legionella and Pneumophila. We have the amplification with the growing inside the cells. So here we have number one is a dead leg going off to for future expansion, and number two is an equalizer line. Neither one of them, do we ever want to drain those to maybe flush them? I mean, are drain lines really, I look on all the jobs that I go, and are drain lines really that hard to put on the equalizer lines? Don't see them very often, so they must be difficult. The dead legs that we see now, particularly, is the redundancy on the redundancy. The large data centers that have to have, X+2 or something. Stand by this and stand by that. And when do those stand by this and stand by that to actually get operated? There we run into a problem. The other issue in dead legs is an existing building. Let's say you have two 300-ton chillers. 30 years old, you want to replace one, and you replace the one with a new modulating chiller, with the turbo core compressors. So you have, really high efficient, they don't use any oil. Which one, if you're an operator and you're dealing with energy, which chiller are you going to run? You going to run that old one? You're going to run the new one? You pretty much are going to run the new one. What's going to happen to that old one? Well, it's going to be happy with little bugs. So here's our guy. Here's a, if I can use there it is. Mr. Blue here has got the operating water level correct. And this is a cross flow tower. It is right at the bottom of the drift eliminators. That is correct application. Most manufacturers, all manufacturers, will design in their cold basin. You can see where these bolts are. There's the bottom, and so they will design in their system shockingly, sloping cold water basins that will flow all the dirty, crappy water down here into the center section. So looking at this, so the water level would be here, about there, about 10 inches or so, and then in the depressed section is where all of the sumps and suction piping are located. Here's our first system one. And here we have 3-cell cooling tower, 3-cell pumps. And typically we would, if we would shut down and we would operate CT1 with chiller 1 And what happens when you operate that in the pumping system, all pumps are parallel piped. Open water system pumps are parallel piped. So that means, as you can see from this sketch, one pump on 750 GPM because, you know, the friction varies as the square, right? The pressure is the square, horsepower is the cube. But so as you reduce flow, you reduce pressure. So therefore, on the system curve, when one pump is on, you're always going to pump more than half, you know, the equivalent of a single pump. So here we have a typical performance curve for those three pumps. And I used 300-ton chillers. And I've got 100-foot of head on there because a few years ago, and this typically a small system like this is going to have 50 feet of head. It's not going to have 100. But if an engineer happens to say, oh, this always happens, oh, my guy over here, the young engineer over here, he calculated 50 feet ahead, but I'll just put a little more on. And then he gets to his boss, and he says, you know, we'll put a little more on. So consequently, you've got oversized pumps, and this is a common problem. So if here we are operating here with three pumps on, there's your 2700. Whoops, back. With just two pumps on, you got maybe 2,300 GPM with one pump on, with two pumps on. With one pump on, dadgummit, sorry guys, 1,500 GPM with one pump. So with just one pump on, out of the three, you're still pumping 1,500 gallons per minute. This is common. Now what happens when you overhead? So now, instead of operating 100, let's say you really only had 80 feet. So you're operating out here. So then the curve goes like, where's my crosser? So then the curve goes here and it comes all the way down like this, right? So this pump over here is operating there. So that's off the pump. Talk about sustainable engineering. That pump operating that far off its system curve is going to have an imbalance on the shaft because your velocity is high. So you're going to be replacing bearings and seals. And you know, most manufacturers don't make money on their equipment today. They make it on the spare parts. So by you, Mr. Engineer, by oversizing pumps, you are saying, thank you, Mr. Pump Manufacturer, I can actually make some money on my equipment. Thirdly, when you overpump, the cooling tower manufacturers like to say, well, we only need a 6-inch suction for this. Well, that's 10 foot per second velocity. So when you overpump and you exceed that 10 foot per second velocity, then that causes bad things to happen, and we're going to talk about that. So overpumping in cross-flow towers is particularly bad because the upper hot water basin is designed with typical nozzle size to maintain say between 2 and 4 inches in that upper hot water basin. So, and that enough transition time to go from the hot basin to the cold basin. If you exceed that, then the upper hot basin does not transition in time, and the pump can, in fact, pump the cold basin dry. So this is a problem with overpumping cross-flow towers. And so here's what happens. So if you overpump, you could, if you've got a well-selected pump, you could, VFD would definitely, be controlled to keep your flow where it should be. You could adjust those nozzles, make them bigger to take the more flow. Or what most facilities engineers do, they just raise the water. Mr. Green just raises the water level. And you can see here, an overflow pipe that Mike Pete and I were talking, where they just raise just a little rubber, little sleeve on there to, get the overflow level up so it doesn't go over the basin. Counterflow towers, just because of their flow distribution system, don't have the inherent problem of overpumping and taking a basin dry. But they are both affected by exceeding outlet velocities, the 10 foot per second. Because then an operator is going to see this vortexing, and he is going to raise the water level. California Title 24 said that if you have only one pump on, one chiller on, you will still send all the condenser water to all the cooling towers. And what this is just basically maximizing the heat transfer surface and slowing the fans down. So if we have a 20 horsepower cooling tower, 300-ton cooling tower, say 20 horsepower, if we isolate to just one tower, one chiller, that's a 20 horsepower fan. However, if we circulate all the water to all three cells and slow the fans down, the fan laws, then all three of those fans are probably going to be less than 5 horsepower. So this is really the reason why California Title 24 set this up, was to reduce the fan loading and save on horsepower. What it does for us, it allows all that water, even if you overpump, you're still spreading the water to all three cells, so you're not going to have the higher discharge velocity. Now, when you shut down, when you have an isolate, because equalizers are to not only balance but to isolate for maintenance, then you're back to that previous system where you've got just the isolated tower, and you can run into the same problems with the raising the water, with the needing to raise the water level. So it does save energy, but here we have the City of El Paso Civic Center, and this is a cooling tower. I've always said, no reason why you can just put it behind if you're going to put it behind an enclosure, just make the cooling tower out of the enclosure. But here we have a stagnant waterfall. Does not look like a healthy place. Okay, equalizers. This is the worst case example where it just says, if you have everything going to one and you're going to suck one dry. Now, the same thing would happen if you have, out of this 800 GPM, if you have 420 gallons per minute going to one and 380 gallons going to the other one, just off by 40 GPM, you don't have an equalizer, you're going to suck one of the basins dry. Equalizers are sized to take that into account, and usually 15 to 20%. Some manufacturers say 20. I use 15. So here for this 400 gallons per minute, they're going to size an equalizer between them to handle 120 gallons per minute. So that would be what, 460 GPM in one and 340 GPM. An 8-inch pipe at 1-inch head differential will flow water. We'll keep it equalized. There's 3 ways you can do it. You can use a bottom outlet. You can use a flume. You can use a side equalizer. And we're going to talk about that. But again, remember the equalization is to balance and isolate. And many times the isolation comes into play, which even with a good design like we had, if you isolate, then the operator may still, I'm going to raise the water level. I mean, it's just like they want to raise the water level. So here we have an equalizer. So on the left, you see there is in this equalizer, there is a drain valve, shockingly. So every now and then, some people do actually put in an equalizer, but it takes a lot of room under there to put this pipe. We got height coming into play. Building codes say you can only be so high in your building, so cooling towers got to come down in order to meet those building codes. So the flume is really the best way. It has large area. It will take large flow discrepancies. But equalizers, I don't like to go inside. I don't want to put that weir gate in. It's too much trouble. I have to go inside. I just want to stay outside and turn a valve. And cooling tower manufacturers have been part and parcel in allowing this, because the side pipe equalizers, they look good, but if you've got an 8-inch pipe just coming off the side, how much free area do you have in there to move any water if there's any equalization of an 8-inch pipe? Maybe 2-inch, maybe 3-inch. I don't know, you swag it. But instead of, if you've got like a 3 or 4-inch pipe and some little water, how much water are you going to be able to get through that? Well, 30 gallons a minute. So you really, the only time side equalizers really should be used is when you don't need the darn things. So why? Here we are. Symmetrical piping. If you do this, the laws of physics say side equalizers don't work, and the law of physics say if you have them piped symmetrically, you're good. Because if you do use side piping and it's not symmetrically balanced, what's going to happen? There's no driving force. In order to get any water through that side pipe at all, where does the water level need to be to get any water through this pipe? The normal operating water level is right there in the middle of that pipe. That's where the normal operating water level is. So if you want to get any water in that at all, this guy over here, looky there, how about a side equalizer getting in through there? Any flow getting through that anyway? Any biofilm growing in that equalizer pipe? So, and I said with greater than 5% flow differential, I just pulled that out of there. I don't think anybody really knows what it really needs, where you really need to be to have if you have unsymmetrical supply piping. In hydronic systems, we use automatic control valves. You know, every radiator will control, but they're only plus or minus 5%. Those flow, and I don't know if a cartridge is probably not going to work. You know, hydronic hot water cartridge is not going to work in dirty cooling tower water anyway. So, all right. So now we've raised the water level. It's way up there. And back in the day, if you have, like I said, if you have a good design system, all that dirty water is going to get flushed into the middle. It used to just be a side stream filter there on the right, primary, secondary, because we wanted to remove the dirt and the foulant to keep it out of the heat exchanger. That's where water treatment is not water treatment, it's metal treatment to keep the heat exchangers happy. So what happened is, instead of the 5% side stream, which would turn the system volume over about once an hour, now we've got stagnant water, and shockingly, the filter manufacturers go, why should I have that 5% when I say, I'll go to 1 gallon per minute per square foot or 2 gallon per minute per square foot of that basin. So now I'm selling a filter that'll pump 400 gallons per minute to keep that basin clean, because you've raised the water level because you're not operating where you are. So you're wasting money. You're totally over-designed, and you should not have to do that. They're not designed as site-specific. They go cheap. Certain designs are less expensive to buy and put in the others. But I put a filtration system on top of Southern California Edison building in downtown Los Angeles, 44 stories up. What was the most common contaminant in those cooling towers? Any guesses? No, well, bird guano is a real good thing to...
Airborne dust.
Tire dust. Tire dust. And tire dust is not... You're going to need a fine micron filter to pick up tire dust. And the other thing is because the higher flow rate systems don't get rid of the smaller particulate, which by gravity will fall to the bottom of the tower, will fall to the bottom of the equalizer lines, and that's going to increase the sediment particulate and nutrients for biofilm. Used to be the filtration systems in cooling towers, which is some Schedule 40 pipe on the sides of the tower. And I always like to put a little hole with holes in it, because the water level out there where the pipe was is only about an inch or two. Just no water out there at all. But I always like to put a hole in the end of the Schedule 40 PVC so you get some flow out the side, so to take care of the stagnant water on the side of the cooling towers. But now you have filtration systems that are costing more than the filters cost because of the high stagnant water. On the right is another typical equalizer system with dead legs, just another picture of place for biofilm to hang out. So one thing that you could do for future problems, in addition to just having a way to drain the system, is have on either side somewhere, because you may have to flush that out with, 50 parts per million of chlorine or something if you've got a contaminated equalizer piping. You should have some way to move water. I mean, Cooling Tower Institute says that you should always make sure that you have adequate flow through an equalizer. So it's almost like the the operators, design engineers, maintenance people need to know, well, maybe I need to actually put more water in one side of the tower than the other. In other words, have physically on purpose put 460 GPM to one tower and 340 to the other, so you do get flow through your equalizing pipe. And just to close, the one thing I'll say is that because of these turbo core chillers, which do take less flow, if you have a 300-ton turbo core, you might have 4 little chillers on there. And so if you've got a control guy that wants to slow his pump down, his condenser pump down to match that turbo core, you don't want to go before 2 foot per second. It's kind of where our rule of thumb is. Okay? Early word might get the worm, but second mouth gets the cheese. All right, we're done. Everybody want to come on up and join me?
The period for stagnant water. Somebody, what you guys keep talking about stagnant water.
Yes.
I shut down every night. Shut down.
Yep. You're right. I think when you say you shut down every night, but you should. But the good engineering practice is you would keep that filtration system running.
Tim Blanche. Obviously, we typically shut down towers at the end of the day. We shut them down all weekend. Are those periods of time, 8 to 10 hours or 48 to 60 hours on a weekend, are those considered problematic for stagnation?
Now, the answer to that question is it depends. The more organic contamination you have in a system, the faster microbiology will consume oxygen in the water, and then you go anaerobic and you open the system up to MIC activity. So you need to be aware of local sources of contamination, like exhaust ducts from buildings, restaurant exhaust where oils are coming into the cooling tower. So as I said, the answer depends.
And good engineering practice recommends that you run filtration systems 24/7. That's the recommendation.
One additional point on filtration, if a filter isn't capturing something, it's worthless, okay? And there are 2 levels of filtration. There's what I call cosmetic filtration that takes out stuff that you can see and stuff that settles. And then there's functional filtration, which is on a much finer level, but that's the filtration. It's the small particles that redistribute, that promote biofilm formation and contribute to corrosion. So it doesn't matter so much in a normal cooling tower, but in data centers where you have high residence time, you need to be filtering on a very fine level, down under 1 micron with absolute filtration media.
Hi, I'm Rick Hayden from Train. I have a question with regard to the low flow. Gary, you mentioned in your last presentation 2 feet per second. Are there design practices with regard to low flow systems where you need to be careful to not go too slow from a standpoint of dropping out contaminants into the piping versus carrying it along with the flow?
It seems to me that there are 2 different scenarios in the system. We have the equalizer piping, and then we have the condenser water system piping itself. And so in the condenser water system, the rule of thumb that I've used in my hydronic days, 2 foot per second. They say in order to keep biofilm from forming, I've read a lot of places recommend a minimum 1 to 2 meters, 3 to 6 foot per second, to keep the biofilm from establishing itself. Mm-hmm. What is minimum flow? 0.7 feet per second. The equalizer line, the 120 GPM through the 15% through the 8-inch equalizer, that was 0.7 feet per second velocity, just the way it turns out. And I've heard that for whatever reason, So,
Okay, thank
does
you.
anybody else have something more on that? It's a really, see, at a certain point, the biofilm are going to be happy because they're going to go, oh, I got some water to move me along, so I can go from here down to here. But of course, what we're saying, I think, and the guys, if we have some flow through that equalizer line, you'll get that water moving so it gets to a biocide or to a biodispersant up in the coal basin, because down below, equalizer lines are, you know. Yeah.
Thank you.
Does that answer your question?
Yep.
Okay.
Thanks.
I'm Shahid from GSA. I have a question to Josh. You touched upon the boilers with aluminum heat exchangers and issues with the carbon steel pipes. So how bad it is, and what is a good solution to address that?
Great question. It's not that it's something that is absolutely overcomable. It just means that the end solution has to be more complex. And it's simply because the chemistry required to deal with aluminum is not the same chemistry you would do to deal with carbon steel. So which do you treat? And it becomes a balancing act. And if you try to treat both, it's more complicated. You need more chemistry. You need more attention to detail. So it's not that it's impossible. It's just you're kind of doing a poor job on both, so you don't get excellent performance on either one of them. Does that answer your question?
Yes, thank you.
All right, that ends our session. Thank you all for attending. Appreciate your dedication to ASHRAE.